what happened was we defined the Fourier transform of L1, and that was easy because if f is in L1, of R, f hat is easily defined since this term here, f hat of gamma, equal the integral f of t e to the minus 2 pi I t gamma dt. Just by the usual properties of integrals, that's less than or equal to the integral of f, which is finite, since it's L1. So if the function is in L1, then it's easy to define f hat. But what if a function is in L2? This seems like a fine point somehow, but f in L2, and recall what that means, that is the integral of f squared to the 1/2 is finite, is a different story. Well, the first question is, why would you want to define the Fourier transform of the function in L2? Why would you want to even define L2? And there are reasons for that, both mathematical and applied. And the applied reason is that so much modeling has been done on energy, which to me is like in the same realm of complexity as love. It's very complicated. But to talk about finite energy signals, so that's a typical model of that as well. Now it turns out that you can't just say I'm going to define the integral as we did here. That integral doesn't exist so easily if the function is an arbitrary function in L2. If you're on a compact set, then L2 is contained in L1. But for the whole real line, it's much more complicated. So there's a very big theorem called the Poisson theorem that allows us to define It allows us to define the Fourier transform of L2. And here it is. So I think even in the second hour, by the way, I've done these night courses in the past. I think I give you your money's worth. I mean, I'm expecting you to work hard. It's not to tell you. But I feel a 5-minute break, and I let you out at 8:30, you're getting your money's worth. If not, complain to me first, and then to the dean. And by the way, there's a homework assignment there for starters. Now, remember, the homework assignment is you give me these problems at the end, sometime in November, or even a little later if you want. And by that time, you'll also have a project you're working on. And you don't do all 5 of them. I'm going to give you probably 50, 60 problems. You pick 20 to do. Okay, so that's the plan. But you've got to do some problems. You've got to learn some technique. Okay.
I have a quick question. So if f is an L1, does that imply that f is an L1 as
No.
well?
In fact, that equation, I did an example of that already today, and when I took the function, it was the characteristic function of minus t to t, then its Fourier transform was like a sink. It was sine of 2 pi t gamma over pi gamma. Well, that turns out to be an L2 function, but it's not an L1 function. Okay, so I'm going to use the fancy words here. There exists a unique linear bijection. Bijection just means one to one and on to. F from L2 of R into L2 of R with the following properties. Now, first of all, we know lots of bijections. We can think of one bijection anyhow right off the bat, the identity map. That goes to that, right? But let's have some properties here. Well, it has the property that every F in L2 of R, the L2 norm of F is equal to the L2 norm of script F of F. Well, G, the identity map also has that. Okay, F with the identity map. And here's where things differ a little bit. For every F in L1 of R intersection L2 of R, and for every gamma, we have a wonderful formula that F hat, that's our usual Fourier transform, which we can define since F is an L1, right? F hat of gamma is equal to this function F of F at gamma. Well, there you go. Sorry? Now, the key part is part C. And it says that for every F in L1 in L2 of R, there exists a sequence Fn contained in L1 intersection L2 of R, for which such that so F minus Fn in L2 norm goes to 0. And now I'm going to look at Fn hat. After all, it's an L1. I can talk about its ordinary Fourier transform. Minus Ff is equal to 0. What's the limit goes to 0? Okay, so this result is actually deep. It's hard to prove. And it's not obvious, even though it's something you want to be true. And it is true. It's just that it's... and you see what we're doing. We're bootstrapping a little bit. L1 is not contained in L2 of R, or vice versa. But if I look at the intersection of them, then it turns out it's dense in L2, so I can come up with a sequence that satisfies this. But I've got a bijection, one-to-one and onto, and that's the guy I'm going to call the Fourier transform. So, this is a hard theorem to prove. If you look at my book, you'll see it takes some long. F is, by definition, the Fourier, the L2 Fourier transform. Okay, so I have to state that theorem just to be honest. A lot of the times we're going to be dealing really with L1 functions, so they're all the same thing. But just for the sake of being honest, there you go. And then there's a wonderful formula, which is called Parseval's formula. Parseval was a French engineer at the beginning of the 19th century, the early 1800s. And Parseval's formula has the following statement. Let F and G be in L2 of R. Parseval did this for Fourier series, where the result is sort of easy. Then the integral of f of t times g of t conjugate dt is actually equal to the integral of, let me say it here. So f of f is by definition the L2 Fourier transform of f. We'll also denote it by f hat. Okay, since we can define it, it's the same as it would be if we were looking at the subspace of L2 consisting of L1 intersection L2. So let's call it L, same thing. So it's f hat of gamma, g hat of gamma conjugate. The reason I have to make a mountain out of a molehill here is that the integrals, if I take a function, an arbitrary function in L2, the integral of f of t e to the minus 2 pi I t gamma dt doesn't a priori exist. It's just an L2. Whereas if f is an L1, it does because of this inequality argument. So Parseval proved this for Fourier series, and it's a remarkable formula. It basically allows us to write things on the time side in terms of things on the frequency side. And I can't go into detail about this right now, but what's even more remarkable is this formula, in some sense, led to distribution theory, and certainly is related to weak solutions in physics. Because sometimes you can't see something. For example, you're studying viscous fluid and turbulence. And so the only way you can make comments on it is to see how it behaves when it's tested against something. So if you think of this as the phenomenon you're looking at, and you think of this as how it's being tested, but you can measure something spectrally, then maybe ultimately you can say something about that. Okay, so again, I'm not going to say anything more about that, but I wanted to state that there's something involved in talking about the L2 Fourier transform of that. And then when you have L2 functions, we've got this formula which we shall use all the time when we do the Wavelet theory. Okay, another thing about Wavelet theory is, in some sense, it's really just Fourier analysis. But it's a very interesting manipulation that people just hadn't done before, even though Fourier analysis has been around for a long time. It systematically relates Fourier series and Fourier transform. And basically, Fourier series and Fourier transform is the same thing, only defined in different groups. In Wavelet theory, one looks at the inherent subgroup nature and milks it for all it's worth. Okay, so let's spend a few minutes on Fourier series, and then I'm going to spend the rest of the talk actually doing something that will prove something, but it's something very substantive, namely the sampling theorem. And the sampling theorem is in some sense going to be the first step to talking about wavelets, a certain type of wavelet. So Fourier series. Let gamma be bigger than 0, and let f be a function defined on the real line considered the spectral domain for the moment. Be 2 omega periodic. Okay, what that means is that is f of gamma equals f of gamma plus 2 omega for all gamma. Okay. Now, if f has certain integrability properties, so if the integral over k of f is finite for all sets, for all intervals k of finite length, then we can talk about the Fourier series in the following way. So let me write this for assume. Sorry, I slowed down maybe more than I was planning to. Sorry. So assume that. Now, by definition, the Fourier series of f is the series S f of gamma equal to f and e to the minus 2 I n gamma over 2 omega. Now, that's meaningless right now. I've written down a trigonometric series. Fourier series means something very specific. It means I can write down a definition for the coefficients here, where Fn is equal to, for all n and z, is equal to 1 over 2 omega, the integral minus omega to omega, f of gamma e to the 2 I n gamma over 2 omega d gamma. Okay, that is the Fourier series of f. And so it's an infinite series, may not converge. We don't know anything about that, even though f has this integrability property. But the real thing that defines it is these coefficients have to look like this. Now you can see that we've essentially put into this definition, and this is the standard definition, we've essentially put in the inversion formula in here. Okay? So anyhow, this is the definition of a Fourier series of f. We want to, and people have been studying Fourier series for a couple of centuries now. One, for its mathematical beauty, but one, they really do give you information about the spectral behavior of what's going on. I mean, if you can look at some phenomenon, you can write down its Fourier series, and you know what the coefficients are, then if these things are zero a lot, then you know that there's very little spectral content for that element of the spectrum. If it's not zero, then you can say that for certain elements of the spectrum, there is something there. Okay, so, and basically, sometimes we can only do spectral analysis. It's very difficult to bring phase into it and that sort of thing. Okay, so as with Fourier transforms, there's a Riemann-Lebesgue lemma, and there's this Dirichlet theorem. Now, the Dirichlet theorem came before the inversion theorem that I stated for the real line, and here's the Dirichlet theorem. So, theorem Dirichlet. it says the following. Let f of b as above, b as above. Assume f is differentiable at some point gamma naught. Why not? Then the Fourier series of f at gamma naught is actually equal to f of gamma naught. No, f at gamma naught. In the sense that the limit as m and n go to infinity of the sum where n goes from minus m to capital N of f of n e to the 2 I and minus n gamma naught over 2 omega is equal to f of gamma. So one of the things we want, I mean, Fourier series wouldn't be very interesting unless they converge the function we were interested in. We want, we've written down a series, we've, in some sense, stacked the deck by having the, building in the inversion formula. But we'd like to know when, in fact, this guy here is actually equal to f of gamma. And you need some conditions on f. It's not always true. In fact, let me tell you something sort of interesting. Are you recording my voice on this stuff too? this is I'm not going to write it down, but it's interesting. Well, it's interesting if you're going to listen to it. There are functions like this whose Fourier series diverge at every single point. They not only don't equal to f of gamma, but the series diverges. And that is remarkable because the following result is true. It turns out you can integrate Fourier series even though they might diverge at every point. So there is this following theorem that says, take f as above, take f as above. And by the way, one of the ways we write that is by that integrability condition I had over there in the far board. That means we write that as somehow L1 of this funny t with a 2 omega down there. I'll explain that later. But take f as above. The Fourier series of f can be integrated term by term. Then, for every alpha and beta in R hat, the integral from alpha to beta of S f of gamma d gamma is equal to the integral f of gamma d gamma from alpha to beta, where the left-hand side, by definition, is the sum Fn, the integral from alpha to beta of e to the minus 2 I n gamma over 2 omega d gamma. this is only remarkable when you think, if you believe me, that there exist functions satisfying the conditions over there of disintegrability on finite sets, on finite intervals, that there exist functions whose Fourier series diverge at every point. And yet, even if you take one of those functions, well, this right-hand side is finite, since it has this, its integral over finite intervals is finite. And not only that, but this left-hand side is finite and equals to it. It sort of blows your mind. And as historical background, a long time ago, the great mathematician Kolmogorov was one of the real great stars of the 20th century in mathematics, and also in many, many fields. I mean, he, in some sense, began probability theory, and he did so much work in mathematical physics, and he did work in our own field in harmonic analysis. He was all over the place. There's a joke that goes, there was a very good probabilist who was being considered for promotion in this country, and someone said, well, where does he rank? And someone said, oh, he's probably 10th in the world right now. And someone said, oh, no. Kolmogorov just died, he's 9th. I mean, Kolmogorov was thought by many to be the absolute best. But he understood, and actually part of that Russian school understood, that L2 was important in this field. So even though you could, in fact, it was Kolmogorov who constructed this function in L1 that diverged, this Fourier series diverged everywhere. But if you look at L2, so these are equal to the set of all functions f from R hat into C, which are f is 2 omega periodic, and for all alpha and beta, the integral from alpha to beta of f squared is finite. That's what L2 is. Then the famous Lucene conjecture is if f belongs to L2 of into the space here, does SF equal F? And this is one of those places you need Lebesgue theory. I have to say almost everywhere. And certainly, when I was growing up, this was not, the answer to this was not known. And then in 1966, Leonard Carlson proved it is true. So he proved that the Lucene conjecture is true. And I actually know Carlson. And I was traveling with him once from Jerusalem to, I forgot where, it was someplace up north of Jerusalem. And we were talking about mathematics because I was listening with great respect. And he said he thought that he's a modest man too, but so this is modesty, but modesty is also truth. He said to me, he said, certain things in mathematics are so naturally mathematics they almost fold into definitions after time. He said, but certain things are somehow marginally mathematical, and they never fold into sort of definitions. He said, for example, my theorem on the Lucene conjecture, that it's so difficult that it's never going to just be part of the dictionary of mathematics. In any case, his proof is of a certain philosophy and point of view. And a few years later, as some of you may know, Charles Huffman, who was an undergraduate here, and got his PhD from Princeton, I don't know what the age is, 16 or 17, I've forgotten. And this is not, he's done so many things, but he gave a conceptually different proof and of this result. It's a very, very deep result. This is heavy-duty stuff. And there are still questions related to this that are up for grabs. But basically, Hal's theorem is one of those landmark results. Okay, now for the rest of today's class and for the beginning of next class, I want to get to sampling theory. Remember I said we're going to integrate Fourier series and Fourier transforms. And this is where it took me a while to get here today, and I moved quickly in the first part of the talk. I had to cover that material. I hope you let it sink in. And letting it sink in is a very active process. It means studying your rear end off. If you didn't know it already, the material. What I want to show you is something called periodization. It leads naturally to sampling, and sampling theory is important in its own right, but it leads naturally, the way I'm going to present its course, to Wavelet theory. So let's begin with periodization. Maybe I'll leave the definition. No, I'll be doing it again. So let's take periodization. Let T be a number bigger than 0, and let F be in L1 allowed. Boy, it's very soft chocolate. The T periodization of F is the T periodic function I'm going to use this funny notation. F, put a little O on the top of it for period, going around in circles. Sub T, because I have this variable T, this period T, rather. And I'm going to let this be F of T minus NT. Now, I'm not going to put down almost everywhere here, but for those of you who've had real variable, this is one of those places that I need almost everywhere. It's not sloppiness. It is sloppiness, but it's sloppiness on purpose. I don't want to obfuscate this. Well, note that F0t is a periodic function made from a function that's in L1 on the whole real line. So I'm wrapping it around. This belongs to L1 of this torus here, since, what do I have to do? I have to show that what I'm about to write is finite. Since the integral, if I look at the integral, well, from 0 to t, it's a periodic function, so I can look at any interval of length t, of f0t. So in order to show this, what this means is that this item here will be finite, right? That's what this means. Well, let's just write it in. This is equal to the integral from 0 to t of sum f of t minus nt dt. Triangle inequality, I have the sum of the integral from 0 to t f of t minus nt dt. Make the change of variables, let u be that guy there. And so that's equal to the sum over n of, and I have f of u du. And when u is equal to that means I'm going from u so 0 there, I go from minus mt up to t 1 minus n. But that's just, since the thing is, I'm just looking, these are just joint intervals. So this is just equal to the integral of the whole real line of f of u du. This is an L1 of r, so it's finite. So I did every detail there, but that's really important. Yes, sir.
So you said triangle inequality, but really you also changed summation and integration. So implicitly you're doing Fubini, right?
Oh, yes, Fubini.
Okay. Yeah, thank you.
In fact, I used Fubini earlier. Forgotten where exactly, and I didn't say it. But
And
in any case, it's sort of remarkable that we look at this periodization, and somehow or another you think, well, you're wrapping that thing around, why should it be finite? But it is because the function f on r is finite.
And what
Now,
has to happen almost everywhere?
Yes.
What happens almost? What
Well,
almost
this
everywhere?
is, I'm defining this function, and so this is a function defined almost everywhere. This function.
So it might diverge some.
Well,
or
it might
measure
not
zero?
exist at some point, yeah.
Okay.
But not for a set of measure greater than 0. And that comes out of this, actually. Once you have this result holding, then you know that. Okay, so now we have a function that's a periodic function, and it's integrable. So in particular, its integral in absolute value over finite intervals is finite. So what is its Fourier series? So if I look at, so given t, I frequently go through a lot of chalk, but tonight it's ridiculous up here. So, I mean, O'Malley would really be angry with me wasting the tax dollars this way. But, the given t bigger than 0 and f in L1 of r, the sequence of Fourier coefficients of this periodic function let's see, is denoted by f0t of n, and let's compute them. Well, what is it? We look at f0t of n. It's a t periodic function, so that means I have an interval of length t, so I'm looking at the integral 1 over t, the integral from 0 to t. My function is f0t of t, and I'm going from e to pi I n t over t dt. Those are the Fourier coefficients. When I defined Fourier series over here earlier, this is exactly the definition of Fourier coefficients. I wrote out the Fourier series of f0. Let me just make that clear. Fourier series of f0t of t is equal to the sum f0t n e to the 2 pi I n t over t, where by definition of Fourier series, you with me? Because I'm maybe going too fast. So yeah, f0 t n is equal to this. And now let's just write out what this is. This is equal to, and again I have to switch limits here. This is equal to the sum, but it's true because of the L1s. This is equal to sum over m. See, I've got a fixed n here. So now I'm going to sum over m so we don't get confused. Of 1 over t, the integral from 0 to t, I'm just putting in what this is, of f of t minus mt.
Plus.
Yeah.
So the Fourier series here, should that be a minus the next one?
Oh, yes. Well, you know, yes, you're right.
Doesn't matter.
And it does matter if you're using both. But the reason I have a plus here right now is because when I defined the Fourier series, I was trying to be consistent. I thought of them. But when I defined the Fourier series, I did it for functions defined in the frequency domain. I had a minus over there. And now, because I'm doing this one in the time domain, I'm doing a plus here.
So that's what I was wondering. So you just have a minus one place together.
Oh, I see. Oh. Okay, so let's, yes. So since I have a choice, let's leave that one there for the minus. Okay? Thank you for picking that. Okay. And so this is equal to e to the 2 pi I nt over cap t dt. And now the interesting thing here is when I let u be equal to this guy here, what do we get? We have t is equal to u plus mt, and I have the sum over m, 1 over t, the integral of, I'm going from minus mt up to t, and I have 1 minus mt of f of u, and then up here I have e to the 2 pi I n, and now t is equal to u plus mt over t du. And so what I get here is I get a 2 pi I n m, which is equal to 1. At this time of the night, I shouldn't be doing this, but the point is, if I do that change of variable, I get rid of the 2 pi I m n m, because the t's cancel. And so this is just equal to what? 1 over t, the sum of the integrals from minus over m, minus mt up to t, almost choked me, t 1 minus mt, and I have f of u, e to the 2 pi I n u over t du. Okay, that's a u, that's a u, that's a u, and that's an n. And I'm summing over m. So that's equal to 1 over t, the integral from minus infinity to infinity of f of u, e to the 2 pi I u n over t du. So that is equal to 1 over t f hat of minus n over t. Okay, so what did we solve here? We solved that if I'm looking at the Fourier coefficients of this Fourier series, where the function is the periodization of the given function little f, I can write down that coefficient in terms of the original Fourier transform. Okay, let me write that down cleanly. therefore, we have f and L1. I get some exercise, stupid. F and L1 of our periodization F0T, Fourier coefficients F0T n, and we computed that F0T n was actually equal to the original Fourier transform at minus n over t. So that's what we just computed. It's all legitimate by making that L1 hypothesis. Now, let's make an assumption. Assume that the Fourier series of ft0 at some point t is actually equal to f0t of t. Okay, this is what we aspire to have with Fourier series. Let's assume it's true for this particular function on the left. And I've just decided, looking at you, as soon as I state this punchline here, we're going to stop for the night, okay? Because I'd like to keep some of you showing up next week. So someone just said, forget it, Benedetto. Anyhow, assume this. If I have f and L1, and then I do have this fact here. If I assume my Fourier series converges, which it does a lot of the time, the Dirichlet's theorem says it will if I have smoothness, and I'll even do it in other cases. Then we have the following remarkable formula. T times the sum over n of f of n plus, t plus nt is actually equal to the sum f hat of n over t e to the 2 I n t over t. Why is that true? Well, this is just my function, my periodization. That part is. Here, I've just cross-multiplied by the t to get that in. I switched the minus signs here, so I switched them over here, too. And so we have just derived a formula which is sort of spectacular because we've written down a formula. We went up through all this machination about periodization, but we've written down a formula which expresses f in terms of f hat. And this is a form of the Poisson summation formula. If I take t equals 0, it has more dramatic input. If t equals 0, what do I have? I've got the t times the sum f of nt is a sum over all integers. And the fact that the integers power group is very relevant here, is equal to, t is equal to 0, the sum of the f hat of n over t. So the only assumption I made here, and it's one we have to think about a little bit, if you're interested in the pure mathematics part of it, but the only assumption I made here is I have an L1 function, I make a periodic function, and I assume the Fourier series converges. If I do that, then I get this formula here, a special case of which is this. And just look at this. It says that if I am looking on the time side, I've got a sum of the equally spaced points. And that's equal to a sum on the hat side of spacing here is t, spacing here is 1 over t. So this is plus on summation. This is a more general form of it. And it's a formula that's abused sometimes. If you read papers, you sometimes see that they'll use it without checking all the hypotheses. But it is true a lot of the time, and it's more or less remarkable, and it comes back to the uncertainty principle again. Because look, the spacing here is t on the time side, and when we go to the Fourier side, it's 1 over t, and the darn things are equal. It's amazing. So I'm going to stop here. Just as I say, I like to keep some of the clientele. Next week we'll begin here. I'll do the sampling formula, and then we'll start talking about Gabor and Wavelet systems. Okay? This is a great formula.